so here's example 2 in section 3.3. I've kind of written down the basics here already, but let's go through them a little bit more detail. All right, so we've seen this problem before in one of our other sections. We found the domain of this previously, but I'll operate with. I don't know why. It's so free these days. Oh. So smart software. Anyway, so we did previously when we found the domain was all real numbers. The way we figured that out is we took our x squared plus 9, we can't factor it. If we solve it, we set it equal to 0, we get x squared equals negative 9. So then when we square root it, we get plus or minus the square root of negative 9, which is plus or minus 3i, which is imaginary, which isn't part of the real numbers. And so therefore, there's no real numbers that make the denominator 0, and therefore there's no poles or vertical asymptotes in the graph, because the domain is all real numbers. Okay? So domain all real numbers, and that explains what I just showed. Okay, so then our x-intercept is found simply by taking our numerator equal to 0, remember? So numerator equals 0, so x plus 1 equals 0, so x equals negative 1. So that gives us our x-intercept at negative 1, 0, which is what I have written right here. And then for the y-intercept, we are plugging in 0 for x. So we have 0 plus 1 over 0 squared plus 9, which leaves us with 1/9, which is how we get this y-intercept, correct? So these are the intercepts. There's my work to prove them. Okay, we already know we have no vertical asymptotes. Let's look at our rules for the horizontal asymptote. So the degree of the numerator is 1, correct? Because we have degree of the numerator equals 1. The degree of the denominator equals 2. As we know, 1 is less than 2. So when that happens, we go with rule 1 for our horizontal asymptotes. And this can be found, this rule can be found on page 2 of your 3.1 notes in this little box right here, okay? So that's where I'm going off of, but you should memorize those rules. So if the degree of the numerator is smaller than the degree of the denominator, then our horizontal asymptote is at y equals 0. Okay, so we've got our graphed in our horizontal asymptote and no vertical asymptotes. We've got an x-intercept at negative 1, 0, and we have a y-intercept at 0, 1, 9, which is 0.1. So I haven't done a really good job of sketching the fact that that point is at 0.1. If you look here at my computer-generated version of this graph, you can see better that it's at 0.1 or 1/9 because it's been scaled so that we can actually see. So that you can see that y-axis has the decimal values labeling it, whereas the x-axis has those bigger numbers. So it's been scaled properly so we can see where that y-intercept is. One concern that people sometimes have with a problem like this is that there's an x-intercept, but we also have a horizontal asymptote. How can there be an x-intercept if there's a horizontal asymptote? Well, horizontal asymptotes are weird, because they do guide the graph, but they can be crossed. So even though the graph crosses the horizontal asymptote here, it still follows the horizontal asymptote when it gets to the end. So it's still important, even though it can cross it. It never crosses, graph never crosses vertical. that's part of the domain it can't be there. But it can cross horizontals. Okay, now how would we figure out this shape here? How would we, on our own, without having this graphing technology, know that it's going to do this little thing and that little thing? What can you do to figure out that shape of the graph? Not me just telling you that that's what it is. This is on your test. You have no graphing calculator. How are you going to know? Plug in points. Perfect. What points would you have to plug in? Well, we don't need to plug in 0 again, because we have a point for 0. But we don't need to plug in -1, because we know that that's our x-intercept. So we can avoid those two numbers. We could go left of -1 and do like a -2. You might want to do more, I mean, you really wouldn't figure out what this graph really looks like without doing several points. So if time is important on the test, then I would say maybe do a couple of points to begin with, if you like estimate it. But then, if you have time, come back to it later and do more points graph. Does that make sense? Anyway, I don't want to spend a lot of time on this right now, so just plug something in, like -4. Here's our equation. So we have -4 plus 1 is -3. And -4 squared would be 16 plus 9. Oh my goodness, these are just teeny tiny numbers. These are kind of a challenge to graph because they're so teeny. So I know I threw the scenario at you of this is on a test, and I probably struck fear in you. I doubt you'd ever do anything like this on a test, right? But it is kind of interesting to see how it looks and how you would plug that in and kind of find those answers, because that would be 16 plus 9, so 25. So -3/25. Anyway, I'm assuming it starts to make our graph curve that way and that way. But those numbers are going to be a challenge to figure out. Okay. Are we okay skipping this? Because it's probably not something you're going to really see most of the time. It's just interesting.